Okay, welcome back, everyone. It's my pleasure to introduce Zi-Xia Song, who was part of a recent breakthrough on Hadwiger's conjecture, but I guess she's given so many talks about Hadwiger now that she wants to talk about something else. And she will, I forgot to say she's from the University of Central Florida, and she will tell us about the Erdős-Lovász Tihany Conjecture today. Please.
Thank you. Yeah, thank you, Stefan, and thank you, Felix, for the invitation. I also want to thank the organizer, and thank you all for listening to my talk. Yes, for Hadwiger's conjecture, I think we gave so many talks in the past, and I don't have really exciting result recently. So this talk is mainly to promote this conjecture. Okay, I will talk about the Erdős-Lovász Tihany Conjecture. So first, I want to all the results proofs to the result on this conjecture will be all elementary. So this conjecture is wide open. So my talk will be easy to everyone, I promise. So all the colorings for the talk here will be proper vertex coloring. So these are standard notation here. What we want to know here, if you are looking for an order cycle, all you need here is to look for chromatic number. If chromatic number is at least 3, then you are guaranteed to have an order cycle. So back in 1966, Erdős observed the following. He said, every graph G with chromatic number at least 3K must contain K vertex disjoint order cycles. Now to see a quick proof here is, all you have to do here is you list all the color classes out. You take a prop vertex coloring with Chi-G many colors, and you list the color classes out. Now you group every 3 together. Now every 3 will give you an order cycle. So you get a K of, at least a K of them. So naturally you want to ask here, can you do better if I lower the chromatic number just by 1? Now, if you think about it, you will see here, you get a 1 obstacle here. The complete graph on 3K minus 1 vertices has chromatic number 3K minus 1, but you don't have enough number of vertices to give you K vertex disjoint order cycles, okay, for this one. So then Erdős asked the following question. He said, if you take 3K minus 1 chromatic graph with sufficiently many vertices, do you have K vertex disjoint order cycles? In particular, when K is 2, you get a 5 chromatic critical graph. Is it true for 2? Galileo observed at that time, this is false for 4 chromatic graphs. If you drop down by 1 more, this no longer works. So I am not aware of his construction. The one I give here is an order cycle. The easiest one you can find is an order cycle. And what you can see here, if you can solve it for K equals 2, then you solve it for the general K. The idea, once again, is simple here. Once again, you take a proper vertex coloring of your graph G, and you list all your color classes out. So this time you are going to be careful because we assume the truth of K equals 2. So you put the first 5 together, then you group every other 3 here afterwards. So this one will give you 2 vertex disjoint order cycles plus K minus 2 here. So you get a K of them. So all you have to do is solve this case. Now, when Lovász tried to, so I quoted this one from the proceedings of the conference published for this conference here back in 1966. Erdős proposed the following. He said, when Lovász tried to solve Erdős's problem, he made the question even harder. Lovász didn't solve the 5 chromatic case, but he proposed a stronger conjecture. So if you take a K chromatic graph which does not contain a complete K-gon. So complete graph on K vertices. You take two integers, which is at least 2, and they satisfy this condition. So then you can split the vertices of a graph G into 2 classes so that the first one, the graph induced on the first one, has chromatic number. So there is a type I called it. So this should be at least A, and the second one at least B. So if you take A to be 3, B to be 3, so this will settle the case for 5 chromatic one. The question, Erdős' question, will completely settle Erdős' question. And Lovász also observed further that for the special case when A equals 2, doesn't seem easy to solve. So you will see more after this talk. So what I want, the conjecture mentioned here now is known as the Erdős-Lovász Tihany conjecture. So for the talk here, I'm going to let S at least 2 T at least to be integers. So throughout the talk, I will assume this. So we're going to define here, introduce one notation. A graph G is ST splittable if the vertex set of G can be partitioned into 2 sets, S and T, such that this one has chromatic number at least S, the second one here has chromatic number at least T. Now the conjecture states that every graph G with clique number strictly less than chi G, which is equal to S plus T minus 1, is ST splittable. So the name of this conjecture was introduced by Jensen and Toft in their famous book, Graph Coloring Problems. So I put a picture here of, this is the city of Tihany. When I first saw this conjecture, I was very careless. I was asking myself here, who is Tihany? I don't know any result of this person. It turns out it's I was very careless there. That's why I put a picture here, just in case if someone was wondering the same thing as I did back in 2016. Now let's see here what we know about this conjecture. So for this conjecture, not much is known. Now, as Stiglitz mentioned in his recent paper here, he says this conjecture seems difficult to attack and might even be false, but no counterexample has been found either. Okay, now when I talk about these special cases, I assume here S here is at most T. Okay. So this case, the first case, 2-2 case is trivial. If you think about it, you see a proof immediately. So the next 2 cases here were settled by Brown and Young back in 1969. So we want to see here this 3-3 case. The solution of this 3-3 case settles answers the question of Erdős. So we know this now. That question has been completely solved. So the next case here, 2-4, was solved independently by Stiglitz and Mosen. Stiglitz's proof was very nice, very short. Sadly, this cannot be extended further to 2-5 case. I don't know how Mosen proved his one because it's written in Russia. Stiglitz later settled 2 more cases, 3-4 and 3-5. And,
sorry, what is omega of G?
The clique number, the size of the largest clique, the size of largest number of pairwise adjacent vertices in a graph.
Oh, thank you.
Okay, this is the clique number. So these are the all known cases in terms of ST here. So it's wide open. Not, as I said, not much is known about this. Here, I do want to mention quickly here some properties of minimum counterexamples of this conjecture. So we define a graph here to be an ST graph if it's connected, and the chromatic number is S plus T minus 1, and which does not satisfy does not give you two vertex disjoint subgraphs with chromatic number S and T respectively. Now a K-clique here is just a set of K pairwise adjacent vertices. So the largest number of such a K is defined to be the clique number. Omega G is the largest K, okay? So just want to show you here, as I said, all proofs here you see here are all elementary. You don't have any fancy tools. And that's why I think this conjecture is hard because we don't have tools, okay? So if you let a GB and ST graph here, if you take any, if you have a clique on S with S vertices, and you delete this clique from your graph G, and this graph here is going to be T-1 colorable. The chromatic number of this one actually is exactly T-1. And you take a prop coloring here of G deleting K, and you list the color classes out. Then for each color class, you must be able to find a vertex from each color class, such that this VI here is adjacent to all the vertices in the clique K. So it's complete to means it's adjacent to all the vertices in K. So in particular here, if you look at the S clique here, this clique has at least T-1 common neighbors. When I say common neighbors, means a vertex is adjacent to all the vertices in my clique K. Now the proof once again is straightforward. So I want to share with you the proof here. It's quite straightforward. Now these are the color classes I had. So these are the color classes. And I on purposely put the V1 here, I prove by contradiction. Suppose I have a color class, let's say V1. V1 doesn't contain a common neighbor of the clique K. So now I can partition the first color class V1 in the following way. I put all the non-neighbors of U1 in a set, I call it the capital U1. After I take away the non-neighbors of U1, now I look at the non-neighbors of U2 and put them in a capital set U2 here. And by the way, all these capital UIs could be empty. Now you find your color classes here. So you look at this one, and this one, and this one, plus this T-2 of them here. And you see your original graph would be S plus T minus 2 colorable, which is a contradiction. So you see this quickly. Now, similarly, you can prove same holds if I have a T-clique of size K. If I have a T-clique, I'm sorry, if I have a T-clique of my graph G and I look at the same property, same thing, the same thing holds for this T-clique K. In particular here, so you see this one, Stibitz proved this. If G contains KT as a subgraph, then a clique number of G here is at least chi of G. I mean, this is, we put it in this way to, I should have put the equation here. I mean, clique number can never go beyond the chromatic number of G here. So from this property, you can see here, if you look at the minimum counterexample, this would be the minimum counterexample to the Erdős-Lovász Tihany conjecture. Then you will see the clique number of G here would be at most chromatic number of G minus 2. Even if I told you the chromatic number of G here is exactly chi G minus 2 here, we still don't have a proof for this conjecture. So recently, more recent work on this conjecture is focusing on certain families of graphs. Okay, so what families are known for the Erdős-Lovász Tihany conjecture here? So let me define some definition here. So we say a vertex V of a graph G is simply sure if its neighborhood is a clique, and by simply sure if NV is the union of two cliques. So we don't know what's happening between these two cliques, but we know the neighborhood can be covered by 2D. So we know a graph is quasi-line if everything is simply sure. And we also say a graph is claw-free if it does not contain K13 as an induced subgraph. So we know Maria Chudnovsky and Paul Seymour give a famous structure results here for claw-free graphs and also for quasi-line graphs. So we knew every line graph here is quasi-line and every quasi-line graph is claw-free. So Sasha Kostochka and Stiglitz, they verified the Erdős-Lovász Tihany conjecture for line graphs. So if G is the line graph of some multigraph which satisfies this condition here, then G contains an S-clique K such that the chromatic number of G deleting K is at least. So in particular, G is ST splittable. So this is stronger than just proving G is ST splittable. So later, Barlow, Kostochka, Prince, and Stiglitz proved that the same is true if my graph G is a quasi-line. So their proof does not rely on the structure result for quasi-line graphs. They give by using the definition of quasi-line graphs. So what else do we know here? So we try to find more families for the Erdős-Lovász Tihany conjecture. So we can try to define the following two families. One is F1 here contains all the graphs G such that every non-null induced subgraph of G. The second one here I define to be non-null induced subgraph of G has a bisimplicial vertex. And we do need this property to be hereditary. So that's why we use induced subgraph here. So are these two families well defined? We don't want them to be too trivial or to contain the graphs we already knew that satisfies the conjecture. So every graph in the first family you can see here is omega G degenerate. So it is omega G plus 1 colorable. But if you knew colorogram, I mean, US graph is color, so it's perfect. So the other graphs in F1 here, so we won't be interested in this family.
So now, what is non-null induced? Non-null induced.
Non-null means you must the vertex set is not empty. The vertex set of the graph of your induced subgraph is not empty. Yeah, it's not induced. Yeah, induced graph means you obtain by removing vertices from your graph.
Thank you.
So this, yeah, so we have this. So we won't study the graphs because they are perfect graphs. Nothing is better than being perfect here. So, but if you look at the graphs in F2 here, in the family, in the second family, it is 2 times omega generate. It is so it's the chromatic number. So it's chi-bonded here. So the chromatic number is at most 2 omega G minus 1. And we also see here, if G is a quasi-line, then G contains in the second family. So we don't want F2 just contains quasi-line graphs. So we want to see, are there other graphs in the second family here? So it turns out to be, yes, there are other graphs. So now we say a hole in a graph is an induced cycle of length at least 4. And a hole is even if it has even length and odd if it has an odd length. Now a graph is even hole free if it has no even hole. So very recently, Chudnovsky and Seymour proved the following. Every non-null even hole free graph has a bisimplicial vertex. So here, it contains even hole free graphs. It contains quasi-line graphs, even hole free graphs. And by the way, we can see here, an even hole free graph is not necessarily claw free. So it does not contain all the claw-free graphs. So you can just want to show more evidence for the conjecture because as I said, this conjecture is wide open. So you can try to see here if this conjecture holds for all graphs in F2. Now, if not, can you at least prove it's even whole free graphs? And you can even narrow down to even for the graphs that are both even whole free and claw free. And I think Chadanovsky, Seymour, I think Alex Scott and Sophie, they have proved this graph click. Even with a bisymbolic click, I still don't see a proof here for this conjecture. So what I can do recently here is the following. If you want to verify the conjecture for the graphs in the in F2, in the formula F2. So this is the graph here. If S here is larger than the chromatic number of G divided by 3, then G is ST splittable. Now from this one, you can easily deduce that if my graph G is even whole free, which satisfies this condition, and if at least which is chi G divided by 3, then G is ST splittable. And sadly, I don't know how to deal with this case when S is at most chi G over 3. So I will give a proof sketch later. Is short. Okay, the proof is short. I think I have some internet. Okay, that's okay now. Now, I just want to say here, the conjecture also holds for more formulas of graphs. So in the Barlow, Kostoshka, Prince, and Stibis proved that the conjecture holds for graphs with independence number exactly 2. And we don't know if it holds for independence number is 3. Okay, is 3. However, if independence number is at least 3, and you forbidden all the between 4 and 2 alpha minus 1, 2 alpha G minus 1, then G is splittable. Now keep in mind here, this graph may have an even cycle of length 2 alpha G, may have an odd cycle of length 2 alpha G plus 1. So you allow 2 more cycles, and you can prove this one is true. And I cannot drop this one to 2 alpha. Now, what about the claw-free graphs? Chadanovsky, Fredkin, and put it back in 2013. So this paper is on archive. For claw-free graphs, they can prove that you can find a click K of size at most 5, but you don't know exactly what is the size. So you only know it's at most 5, such that this is true, such that this is true. So their proof relies on the structural result of claw-free graphs. And so this ELTC is still open, is still open for claw-free graphs. So that's pretty much all known of Erdős-Lovász Tihany conjecture. So now I want to mention a weakening of this conjecture. Before that, let me mention a nice relaxation of using a coloring number of a graph. So Stibis proved that you can almost prove it, but this one is replaced by the coloring number of a graph G. So if you can improve this one, if you can replace one of them by replace this one by chromatic number, you settle the conjecture. So for this nice relaxation. And also I want to mention the special case. This is when S equals 2. So when S equals 2, you are asking for an edge in your graph, so that if you remove the 2 vertices of the edge, the resulting graph is at least is at least chi-g minus 1 color to color. So if you prove this one by taking a minimum count example, then your graph G must be connected. Then chromatic number of this one here of G deleting XY must be chi-g minus 2 for every edge. So this motivates the definition of double critical graph. I'm sorry, time is up. Can I use 2 more minutes?
Yeah, if you can wrap up.
Okay, I will wrap up quickly. So this is the that's how we come up with double critical graphs. So if you double critical means deleting any 2 adjacent vertices, the chromatic number is decreased exactly by 2. So the only known cases is the complete graph. So no non-complete is known. So this is now becomes the double critical graph conjecture. Which states that the only double critical K chromatic graph is the complete graph KK. And this one is wide open for K is at least 6. Now it's hard because we know every edge belongs to many triangles. You see triangles everywhere, but we cannot prove it has a K4. So we cannot prove this one. So another weakening here, I should mention let me skip this one. We know Hadwiger's conjecture. So we put a quotation mark on the weakening here. It's not really weakening. It means if Hadwiger's conjecture is true, then the Erdős-Lovász Tihany conjecture becomes the following. So any graph satisfies this condition should contain 2 vertex disjoint graphs G1, G2, such that the first one contains Ks as a minor, the second one contains KT as a minor. And not much is known about this conjecture either. Okay, and last one here, let me wrap up quickly about the minor version of double critical graph conjecture. So for this conjecture here means every double critical K chromatic graph has a KK minor. Now this has been verified to be at most 9. It's wide open for K at least 10. Sorry, I overused this one. I didn't keep my promise to give you the sketch of the proof. I want to thank you all for listening.
Thank you, Zi-Xia. Let's give you applause.
Sorry, what is Hadwiger conjecture?
Yes, I'm sorry, I speak too slowly. At the beginning, I didn't get a chance to. I do have. So you know what is a minor, right? So the minor of G, if the graph can be obtained from subgraph of G by contracting edges. Okay, so Hadwiger's conjecture says that every KK minor must be K minus 1 colorable. So you are asking what stops a graph to be K minus 1 colorable? It's not the troublemaker is not the complete graph. It's not the subdivision of KK. They believe, Hadwiger believes it's the minor, complete minor on K vertices. So this is the Hadwiger's conjecture.
Thank you.
You answered already my question who this Tihany is. I was wondering. So is there any other question? So what if you restrict the click number even further? Does this make sense, or?
No, as I said, if I can allow you to have a chromatic number at least chi-g minus 2, I still don't see a proof. As I said, we don't have tools. So Schlibius is the expert on this conjecture. His proof for 2-4 case is very nice. But sadly, you cannot apply it further to the other cases. I wish I speak Russian, I can read Mosen's proof. I don't know how his proof went. Maybe it has good ingredients, but conjecture overall is wide open. We don't have tools. I've been trying very hard to look for K4 for the double critical graph conjecture. It's Well, this conjecture, yeah, for this one, I did not get anywhere for this part.
Maybe
Look for.
maybe our organizer can help you with the Russian article if you.
Yeah.
Yeah.
Okay.
As I said, this talk is mainly to promote this conjecture. I hope more people will be interested
Yeah.
in this.
Thank you for doing this. Let's give another
Thank
round of applause.